Hello, calculus scholars. Today, we're going to kind of learn the properties of integrals. So this is scale 37. So one of the things that I will say will go back very early on in your math career. When you were in kindergarten, first grade, you learned about like numbers. So early grade school, you learned about numbers. And a few grades later, you learn that you could like add, you could subtract, you could multiply and divide. And then like kind of in middle school, you started learning about, variables like in algebra class. And we learned that we could, subtract, add, multiply, and divide, do things like distributive property. And then early in calculus class, we learned that the same properties exist in, limits and derivatives. So the question is, can that extend to integrals? And I think what you'll see, and we could probably predict, that answer is yes. I just want to kind of clean some things up here. This is a review of integral notation. So we call B our upper limit of integration. We call A our lower limit of integration. And the geometric interpretation of an integral is that this represents the area between the curve or the function and the x-axis. So you may want to pause there and make sure that you are good with the notation. All right, so what we're going to kind of start with are some properties of integrals. One of the most obvious properties is that if you have the same starting and ending x value, the same upper and lower limit of integration, this is property number one, then obviously, it's kind of like, no time has passed. So obviously you cannot have any area accumulated. So that is equal to 0 every time. All right, let's say that we have a x value of c that's between a and b. What you can do, and we've actually seen this a little bit already, is that this is the same thing as saying that the integral from a to c of f of x plus the integral from c to b of f of x. So you can kind of chunkulate two integrals together. All right. The next property here says that if you flip the limits of integration, so if the integral from a to b is equal to k, then the integral from b to a is equal to negative k. So flipping upper and lower limits. Flips the sign. All right, and then this one says, given that b is less than a, if you have that type of situation, then So if we have that type of situation, then what we can simply do is flip the limits of integration and then put a negative sign. So we can say, as a result, that we have the negative b to a of f of x dx. If we have a constant, we can put that constant in front of the integral and then actually evaluate the integral. If we have like a plus or a minus type of thing, we can actually chunkulate the two integrals. So this would be like the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. If we have an even function, one of the things that you can actually do just to make life easier is you could actually just do this is the same thing as doing 2 times the integral from 0 to a. So it's symmetrical here, so you want to use symmetry. And then you would have f of x dx. And then if we have an odd function, so like let's say I'm kind of like shading my area here, so that's a plus. And then I'm going to shade a comparable area here. That's minus. So if we have an odd function and we have the positive and the negative version of the x value, then that integral is also going to be 0 because they effectively cancel out. So for these, you want to kind of be thinking about use symmetry. All right, let's actually look at some equations now. So one of the things that we can do actually is kind of give you some information here, and you can actually be thinking about using the properties. So I just care that you're systematically going from one step to the next. So here's what we know. We know that the integral from 0 to 3 is equal to 6. And then we know that the integral from 3 to 7 is equal to negative 8. So on this one, it's basically the flip of 0 to 3. So if I put a negative sign, this would be equal to negative the integral of 0 to 3 f of x dx. But the good news is that this is already given to us. So we can just say that this is negative 6. So we like sequentially using the properties here. Let's say that I want to integrate from 0 to 7. Well, it turns out I know 0 to 3, and I also know 3 to 7. So why not just say that this is going from 0 to 3 of f of x dx plus the integral of 3 to 7 of f of x dx. And then I'm just going to kind of use the given piece of information here. So what we see is that this is going to be 6. And then this integral is going to be plus a negative 8. And that gets us a grand total of negative 2. I love this third one over here. So the integral has a same upper and lower limit, is always going to be 0. No questions asked. On this one, this combines multiple properties. So you're going to pull out the 3. And I have 7 to 3 of f of x dx. But what I can do is I can actually put a negative sign. And I'm just going to circle that negative sign. And I'm going to flip the integral. And I'm going to go from 3 to 7 of f of x dx. So I'm going to have a negative 3 times a negative 8 to get me a positive 24. All right, this one, we have an integral of a constant here. So I'm actually just going to separate this here. So I got 3 to 7 of 2 dx plus the integral of, I'm just going to pull out the integral, yep, of 3 to 7 of 3 f of x dx. So what I'm going to do here, we can kind of make an observation that we are 2 units high going from 3 to 7. So this is a rectangle that's 2 by 4. And we're going to learn a shortcut the next question for this. And then I'm just going to pull out a 3 here, and I'm going to go from 3 to 7 of f of x dx. So this is going to be equal to 8 plus 3 times negative 8. That's going to be 8 minus 24. And that is equal to negative 16. Now here I have an even function. So this would be equal to 2 times 0 to 3 of f of x. Unfortunately, we already know what that integral is. So that's equal to 6. For a grand total of 12. And then when we have an odd function and it's symmetrical, then that is automatically going to be 0. So those are property of integrals when it just comes to like equations. Now let's actually kind of take a look at a graphical example too. I really like this graphical example here. What I would kind of do immediately is I would just kind of shade things up, and I'm just going to kind of do them one at a time. So the first example here is going to be going from 0 to 3. So I'm actually going to shade from 0 to 3. We got that. And I'm just going to kind of trace this here. And I'm breaking it into kind of familiar geometric shapes. So I like to think of this as a quarter of a circle plus a rectangle plus a triangle. We're not, writing for the AP exam, but I do think it's kind of nice to think about what's going on geometrically on this. And I can actually write out the geometric formulas. So this is going to be pi, and then it's going to be a 1/4 pi times 2 squared plus I got length times width here. So that's going to be 2 times 1. And then my triangle is 1/2 times 1 times 1. So this is going to just be pi plus 2 plus 1/2. So you could just think of this as pi plus 5/2. Or I'll take, like pi plus 2.5 as well. And then you can just kind of keep it in that form. And that's about as simple as you can go. All right, the second example, I'm just going to kind of use a different color. Maybe I'll use blue for like going below. So what happens here is I'm actually going to take, for this, I had for the original problem, so the red part, and I'm just going to kind of see what's going on here. So I have pi, and I can kind of use calculations that I've already done before, plus 2 plus 1/2. but we kind of see that we have a little symmetry, so we're actually going to minus that 1/2. So I'm just going to put that in blue. And these cancel out. So you would just be left with pi plus 2. All right, and then last but not least, then we're going to be doing 3 to -3. So one thing that is kind of nice that we see here is that it is symmetrical. So we can use the property that this is equal to 2 times the integral of 0 to 3 of f of x dx, which was a lot more manageable to find. So if you do 2 times pi plus 5/2, that's actually going to get us to 2 pi plus 5. And you may want to kind of put like unit squared, but they kind of just have you kind of work out what the areas are on your delta map. So we're just going to kind of look at the ones with just like our conventional integral notation on these delta map assignments. So this does give you, most of the useful properties that are going to be, pretty helpful going forward. And you'll just kind of see these properties over and over again.